In this example, it is asked to use cylindrical coordinates to find the volume of the solid that lies between the paraboloid z equals to x squared plus y squared and the sphere x squared plus y squared plus z squared equals to 2. From the figure, we see that we have to find the volume that lies between the sphere x squared plus y squared plus z squared equals to 2 and the paraboloid that lies inside the sphere z equals to x squared plus y squared. So essentially, we need to find this volume that lies between the sphere and the paraboloid. Since we see that z is the axis of symmetry, then that means that we can use cylindrical coordinates. The first thing that we need to do is we need to set up the region of integration, and we see that in cylindrical coordinates, the solid region E is bounded below by the paraboloid z equals to x squared plus y squared, which is equal to r squared, since x squared plus y squared is equal to r squared, and above, and is bounded above by the sphere x squared plus y squared plus z squared equals to 2, which means that since again x squared plus y squared is equal to r squared, we have r squared plus z squared equals to 2, which means that z squared is equal to 2 minus r squared, and that gives us that z is equal to just the positive square root of 2 minus r squared, since we are using only a part that lies in the upper hemisphere. We also need to find the intersection between the curve of intersection between the sphere and the paraboloid, and to do that, starting from the equation of the sphere x squared plus y squared plus z squared equals to 2, we have to substitute z with the equation of the paraboloid, z equals to x squared plus y squared. So that will give us that x squared plus y squared plus x squared plus y squared to the square is equal to 2. And again, since we know that x squared plus y squared is equal to r squared, we'll have r squared plus r squared to the square, which is equal to r to the fourth, is equal to 2. And bringing everything to the left side will give us r to the fourth plus r to the square minus 2 equals to 0. And factoring that, we get r squared plus 2 times r squared minus 1 equals to 0. And from the two roots, r squared plus 2 equals to 0, this doesn't give any real values. So we will only consider the r squared minus 1 equals to 0, which gives us that r is equal to 1, since r should be positive. And therefore, the region of integration E will be the set of all points r, theta, and z, such that since we work with a whole volume that lies in all octants, we'll have that 0 is less or equal to theta less or equal to 2 pi. And also that 0 is less or equal to r less or equal to 1. And for z, we know that z lies between the paraboloid and the sphere. So the paraboloid has equation r z equals to r squared is less or equal to z, and this is less or equal to the equation of the sphere, which is equal to square root of 2 minus r squared. And therefore, the volume will be given by the triple integral over the region of dv, which is equal to the integral from 0 up to 2 pi for theta, and the integral from 0 up to 1 for r, and the integral from r squared up to square root of 2 minus r squared of r dz dr d theta. So that is equal to the integral from 0 up to 2 pi and the integral from 0 up to 1. And we now need to evaluate the inner integral, which gives us integral of r dz is equal to r times z. Z needs to be evaluated between z equals to r squared and z equals to square root of 2 minus r squared times dr d theta. And that gives us the integral from 0 up to 2 pi, and the integral from 0 up to 1. And now we have r times z, which is equal to square root of 2 minus r squared, minus r times z, where z is equal to r to the square, will give us r to the third times dr d theta. So from the first term, we'll have, we need to do a u substitution. So substituting u with what we have underneath the square root, 2 minus r squared, that will give us that u du is equal to negative 2r dr, which will give us that negative 1/2 du is equal to r dr. So therefore, we'll have the integral of negative 1/2 u to the 1/2 du, which gives us negative 1/2 times 2/3 u to the 3/2 if we evaluate, and then plus c. And if we simplify, we'll have negative 1/3 from the negative 1/2 times 2/3 times u to the 3/2, which is equal to 2 minus r to the square to the 3/2 plus c. And therefore, if we plug that back in, we'll have that this is equal to the integral from 0 up to 2 pi. And the integral of r times the square root of 2 minus r squared will give us negative 1/3 2 minus r to the square to the 3/2, which we just found. And then integral of negative r to the third will give us a negative 1/4 r to the fourth. And that needs to be evaluated between r equals to 0 and r equals to 1 times d theta. So that gives us the integral from 0 up to 2 pi. And for r equals to 1, we get a negative 1/3 2 minus 1 to the 3/2, and then minus 1/4 r to the fourth, which is for r equals to 1 will give us just negative 1/4, minus for r equals to 0, we'll get negative 1/3 2 to the 3/2, and then minus 0 for the negative 1/4 r to the fourth for r equals to 0 times d theta. So that gives us integral from 0 up to 2 pi. And then we have negative 1/3 from the first term, negative 1/4, and then plus 2 square root of 2 over 3 times d theta. So that gives us, if we evaluate this integral, we'll have negative 7 over 12 from the negative 1/3, negative 1/4, plus 2 square root of 2 over 3 times theta, which needs to be evaluated between 0 and 2 pi. So that will give us negative 7 over 12 plus 2 square root of 2 over 3 times 2 pi. And this is in cubic units, since we are talking about a volume.